my name is Joonas, and I'm here today to talk about Game Boys. So, I'm pretty sure many of you recognize this device. It's an original Game Boy from 1989, also known as the Grey Brick or DMG dot matrix game. This little console started a console family that ended up basically winning the handheld console wars in the 90s. And yeah, the console line was hugely popular. So, let's talk about the Game Boy console family. So, this is the first console in the family. In total, there were 11 models released, all the way until 2005. One way to categorize these different models, and also the games themselves, is to divide them into these three groups. So first of all, we have the original Game Boy. There's the original hardware, original instruction set in the CPU. Many people think that the Game Boy uses a Z80 processor, and this is actually incorrect. It's a custom processor that has a lot of similarities with Z80 and 8080 as well, but it's not either one of those directly. After the original Game Boy platform, we got the Game Boy Color, which was basically an incremental upgrade. So we got color and some minor hardware features. And at this point, the compatibility between the software and hardware gets a bit complicated. So Game Boy Color games can either be Game Boy Color only games, so they only work on the new Color and later models, or they can be just Game Boy Color compatible. So if you play it on a Game Boy Color or later model, you get some extra things like the color or some other features. Finally, we have the Game Boy Advance, and at this point, we got a completely new hardware platform. So Game Boy Advance games are actually based on ARM instruction set architecture and completely new hardware otherwise. And those games are therefore not backwards compatible with the older models. Game Boy Advance consoles can still play the older titles because they actually have a Game Boy Color core inside the CPU, so they can still run old things with some minor exceptions. Okay, just to show the compatibility in a different way. So in the rows we have the hardware, and in the columns the different software. So for example, the original Game Boy hardware can play original Game Boy games and some Game Boy Color games, but not Game Boy Advance, and so on. So from this table you can see that Game Boy Advance is sort of the most attractive hardware because it has full backwards compatibility and can play Game Boy Advance games. All right, so it's 2018. How are Game Boys relevant today? Well, Game Boys are still very popular among emulator developers. So when somebody new to emulation scene goes to some internet forum and asks, what should I do? What platform should I emulate? People usually first say that emulate chip 8, which is very simple, and after that do the Game Boy. People think that Game Boy is very easy, and it is very easy to get into, but the devil is in the details. There's a very active homebrew and modding scene as well, so we still see homebrew unofficial releases of Game Boy games every year. And I'm not just talking about random ROMs on the internet, actual cartridge releases, not by Nintendo, so completely unofficial, but yeah, you can buy a physical copy of a homebrew game and play that on your real Game Boy. So after almost 30 years, a lot of hardware research has been done. The first emulators were not very accurate, couldn't run all the games, but we've been getting better emulators all the time based on people's hardware research. So the hardware details are quite well understood at this point. But I said quite well. So we can ask this question: do we have a complete understanding of the Game Boy hardware? Another way to ask the same question is that can we build an emulator that behaves just like real hardware? And another way to rephrase this question is, can we build an emulator which cannot be detected with a test ROM? And the answer is no, at least not with publicly available documentation. There are still edge cases and things that emulators don't emulate, so it's quite easy actually to build a test ROM that detects an emulator. Let's talk about MOONEYE GB. MOONEYE GB is my Game Boy emulator project. Right now I'm only focusing on the original hardware platform, so I don't support Game Boy Color games or Game Boy Advance at all. The work started in 2014 because, just like many other people, I wanted to build an emulator, and I've owned a Game Boy since 1997. So I thought, yeah, why not Game Boy? It was recommended as being easy. But eventually I found that the documentation was quite lacking, and in some cases I had more questions than answers. So I shifted my focus to hardware research instead, not just implementing stuff based on existing documentation. So today, MOONEYE GB has very difficult, quite detailed hardware tests that are based on real hardware research and validation. So I've basically built a huge number of tests that pass on real hardware, and you can run those same tests on emulators to validate how well they emulate hardware features. And today, no single emulator passes all my tests, but real hardware does. Some people might ask, so we can already run Pokemon. That's the most important Game Boy game. So what's the point in doing any of this? Well, firstly, in my opinion, all official games should be runnable. There are still some games that don't run on emulators properly. So we would like to have 100% support, at least with official games. In addition to official games, we would like to support existing homebrew and also future homebrew. It's still an active scene. Those games keep coming. So we would like to support those games so that they can be executed on emulators, but also to support the development. And if there's an accurate emulator, it really simplifies testing, shortens your feedback loop when you're developing some software for the Game Boy. You don't need to fiddle with hardware, you can just quickly test with an emulator. But if the emulator is not accurate, you might get false positives or negatives. Imagine spending, let's say, 100 hours building some really cool Game Boy game and just using an emulator to nicely develop it, and then you run it on real hardware and it just crashes, it doesn't work. That would be really annoying. So an accurate emulator is a good tool. Speedrunners also care about accuracy. Pokemon speedrunning is a very serious business. They really care about these details. Also, there's the preservation point of view. There will be a day when all Game Boy hardware is dead. So we would like to fully understand the hardware so that we can preserve it in different form, like a software emulator or some FPGA-based system. And at least for me, research is fun, even though it's very difficult. So during these years, I've built a lot of knowledge on how to do things, electronics and printed circuit board design and stuff like that. I didn't have that knowledge at first, so it's been difficult, but it's very rewarding for me. And one thing that I like about the Game Boy is that I can imagine like a 100% completion where the research is done. It's sort of not an infinite process. Here's a very classical case example of emulators versus real hardware. This is already partially solved, so some emulators don't have this problem. But the game Pinball Deluxe, it's a very lovely pinball game. If you run it on most emulators, you get the result on the left. So basically, after the game starts, it just crashes after a while, and that's it, game over. On real hardware, it of course works. It's a real official game, released game, so yeah, they have tested it. And even though it hits some nasty edge cases, it doesn't matter on real hardware, which just works. Just a quick look at the Game Boy models. So as you can see, there's a lot of handheld devices. But in addition to the handheld consoles, we have the Super Game Boy, the Super Game Boy 2. These are basically a way for you to play Game Boy games on your Super Nintendo or Super Famicom. And finally, we have the Game Boy Player, which is basically the same idea, but for GameCube. So you stack your GameCube console on top of this Game Boy Player, and then you can play Game Boy games. Let's talk about the Game Boy CPU chips a bit. So firstly, let's just think about the Game Boy and Game Boy Color platforms. So we'll still include the Game Boy Advance chips, but only focus on the backwards compatible side of that. So one nice thing about the Game Boy is that one central CPU chip handles pretty much everything. This is quite different to some other consoles. For example, the Super Nintendo, the original version, had 2 pixel processing units, PPU1 and PPU2, separate chips, and the CPU was once again separate, and the audio is separate. Yeah. So many different chips, and if you want to emulate all that stuff, you need to understand how the chips communicate and what's going on between them. On the Game Boy, basically one chip handles everything. And the instruction set architecture is the same. The basic hardware is the same on all models. So we can make this nice assumption that the deterministic behavior pretty much depends only on the CPU chip. So if we give it the same inputs, we always get the same outputs back. And inputs are like stuff coming from the game cartridge, user input, pressing the buttons, and, for example, serial data. Okay, so it's a very nice assumption. It lets us to simplify things a bit. However, it's not completely true, because the mainboard versions and even individual units can have differences. One thing that might differ in this is analog behavior like audio filtering. For example, the original Game Boy model, this gray brick, is often considered to have the best bass in the audio, the boomiest bass, and the later models just couldn't get the same, don't have the same feel. So this could be caused by like audio filtering things on the model. Also, there's this like semi-random behavior, like static RAM initial values. So when you power up the Game Boy, what's inside the main RAM? Well, it's random in the sense that you can't really predict what's they're going to be, but it's not random as in you couldn't emulate it with just calling math random and filling the memory with that. Instead, there's some patterns in the RAM. So some bits tend to be zeros, some bits tend to be ones, and so on. So not fully random, but still not predictable. So this is also not deterministic. But for the most part, it doesn't matter. One way to categorize these different CPU chips that appear on the Game Boy devices is to divide them into generations depending on the pinout. So all the CPU chips we are interested in are QFP chips, so quad flat package, basically the typical rectangle black chips. And the first generation starts with 80 pins. Second generation just shuffles the pins around so they are not compatible but keeps the same amount. And then later models just add more pins. By the way, the 3-letter uppercase things on the right, those are the code names for the individual models. I like to use the code names because they are very short and very specific. So if you know what the code names are, you know what device is being talked about. And there's actually generation 6 as well, but that uses a BGA chip, ball grid array chip, which is basically impossible to analyze or study in like hobbyist environment. And also it's not backwards compatible, so it's Game Boy Advance only. So we'll just forget about that. Okay, so let's say you've built an emulator with the current documentation that you can find on the internet. Which CPU version are you actually emulating? Are you emulating the original DMG CPU found in this device, the first version of this device? Or the next one that still has the DMG CPU label, but there's some differences in the labeling? Or maybe the version A, B, or the globtop version, which doesn't have the normal QFP packaging? Or maybe the C version? Or maybe you're emulating the Super Game Boy? Or maybe it's a Game Boy Pocket CPU, or Super Game Boy 2 CPU, or one of the Game Boy Color CPUs. Or maybe you are focusing on the Game Boy Advance, the backwards compatible side of that. So maybe it's one of these. Except the last one is the BGA chip that it is not backwards compatible, so we'll just forget about that. So in total, there's around 20 different versions that you could be emulating. Most of the time they have exactly the same behavior, but there are minor differences in very deep technical details. And just to show that it actually matters in some cases, is there's a very popular audio test ROM that checks that the audio processing unit behaves as expected. And if we run it on the first and second generation devices, on the really original first version, of the original Game Boy CPU, it works. On the next version, it stops working. Then it starts working again. And in the C version, it stops working, and from there on, it doesn't work anymore. These are in release order, by the way. So the question is, if you have an emulator and your emulator passes this test ROM, which one of these CPUs are you actually emulating? And we could also ask, which version should we emulate? What's the most desirable? Is it the most popular chip, or maybe just the last version, which in this case is the one that doesn't pass the test? And real hardware has backwards compatibility issues as well. For example, if you run the game Donkey Kong Land 3 on a Game Boy Color or any later model, in some levels, the sprites have these weird glitch lines in them. This is really annoying because many of the later models are basically the best Game Boys to play games on. But yeah, then you have these glitches. So you have to revert to these older models if you want to have a glitch-free game session. So the solution is just research everything. So here's a photo of almost all of my Game Boys. It's a bit of an old photo, so there's some have been dismantled, and there's some new ones. So all the MOONEYE GB tests that I've created are verified on real hardware, all the versions I own. And I own all the CPU versions, all the 20. There are some prototype versions that also exist, but I don't care about those because they are basically crazy expensive and normal Game Boys don't have those. So then let's talk about some hardware research tools. So how do I find information about the Game Boy? How do I research it? Well, the simplest way is to have a flash card and flash some test ROMs on it and then run it on real hardware. Just test things. So here's two flash cards. On the left, we have the EMS64M card. I think this is one of the cheapest options available. It's not visible clearly in the photo, but it has a USB port in the top. So you take the card, plug a USB cable, and you can just flash a ROM there. But you can't do this while the Game Boy is running or it's connected to a Game Boy. So you need to unplug and plug cables or the card itself all the time if you want to modify the ROM. So that's why I created the GB Live 32 card on the right. It also has a USB port, but the idea with this card is that you always keep the USB cable there. And with you can just run one command on your PC to update the ROM live and reboot the system without touching any cables or anything. So it basically just gives me a much shorter feedback loop. Another way is to probe the CPU, use a logic analyzer, some oscilloscope or something like that, or even solder to the CPU pins if you don't care about it being slightly invasive. For this one, I also have some custom hardware. So on the left side, we have the mail breakout cartridge that you insert to a Game Boy, and it just gives you a nice, simple way to access all the cartridge bus pins. And on the middle photo, in the middle photo, we have the male and the female breakout board together. So this gives me basically a pass-through system. I insert a real cartridge in one end, and the other end goes to the Game Boy. And in the middle, I have all the pins. And I can just probe those or use an oscilloscope or something like that. In the last photo, you can see one of my setups for researching things. So there, on the table, there's first a Super Famicom, so basically a Japanese Super Nintendo. In the Super Famicom, there's a Super Game Boy 2, and in that Super Game Boy 2, there's both of these breakout cartridges, and then there's the EMS cartridge, and everything is connected with a lot of wires to logic analysis and stuff, and there's a debugging dock as well. So this is actually how I dumped the Super Game Boy 2 boot ROM, which is an internal program that is the first thing that executes when you start the Game Boy. Okay, these are still fairly limited. So if we go with a slightly more invasive approach, we can just desolder a CPU and put it on a custom test board. So I've got another board for this. So this is the GB Bench G1. G1 stands for Generation 1. So this accepts any Generation 1 CPU, and it's basically a full Game Boy, but it has some debugging features in it. So it's a 4-layer PCB, something that I ordered from China. Not crazy expensive, but yeah, not that cheap either. There's a full first-generation Game Boy on board. It doesn't have a screen, it doesn't have a joypad or a speaker, but all the signals are there. So I could create some extra boards and plug them in, and then I would have a really, truly full Game Boy. There's two lattice CPLDs, which are basically programmable logic devices that give me full bidirectional access to the CPU pins. So at any point of time, I can read what are the signals in the pins of the CPU, and I can also write some things when it's relevant. And all this uses this parallel control bus where I can plug in like a controller board, which currently is basically a Teensy 3.6 based controller board. So this is the hardware. On the software side, I've got automated tests written in Lisp. I don't really actually like Lisp. It was just easy to integrate into the system. But so I've got these low-level tests that I can run on any board and basically on any first-generation Game Boy and check the results. I can also capture signals, output CSV files, VCD files, value change dump files, or capture the frames that would be shown on the LCD as PNG. So I've got full control. I can see everything that's visible externally to the CPU. Okay, I was supposed to have a demo today about this, but unfortunately my board just blew a fuse. So I'm just going to show the board. So the big board is the main G1 board, and the small one is basically just something where you plug in a normal Teensy 3.6 board. And there's a USB connection, so that goes to the PC. All right. If we move on to even more invasive techniques, we can also decap the CPU chip. So open it up and see what's inside. And this photo is from the Silicon Prawn website. So it's a website that has a lot of decapped photos of various kind of chips taken with really expensive equipment. So by spending a lot of time on analyzing these kind of photos, we could reverse engineer the transistor layout, the very, very deepest, lowest level details in the chip. Unfortunately, at the moment, we only have like top layer, the top metal layer photos, and the real chip is actually has multiple layers. So right now, it's not possible to get the full transistor layout. We can only see the top things, but we can still see how things are connected. So here's the same photo in a bit bigger form. Let's just fade it out a bit so we can highlight things a bit easier. Let's add all the pin labels. They are a bit small there, but yeah. And here are the VCC and ground nets. So basically the power and ground connections. And if we just add all the connections from the pins, so we can see where things are going. We can even add some internal connections that I've traced. So there's a lot of connections there. Maybe it's better to just focus on some smaller things if we want to understand the chip. For example, we could just highlight the video RAM and the LCD signals. And from those we can see that they tend to go to this area in the bottom left. So that's probably the PPU, the pixel processing unit, because that's the part of the chip that cares about these signals. We can also highlight all the data bus signals and some control signals, and we can see that most of them go to the top left, and there's also another area in the middle, top middle. So these are probably some kind of bus control areas, because bus control logic would care about these signals. Okay, there's another part we could take a closer look at, and it's this tiny ROM area here. So it contains a small Game Boy program, and we know that it's actually the boot ROM. We can enlarge that a bit. So you see those tiny white or light dots. Those are the individual bits. So if I knew the pattern, which I actually don't, I could read out all the bytes in the boot ROM just by visually inspecting it. But yeah, I don't know the pattern. It's not the obvious left to right, top down pattern. But somebody else has done this already, so I don't even have to do it. Okay, a bit more about the boot ROM, since we just looked at it. So first of all, there's actually several boot ROMs. Different models sometimes have different boot ROMs. The first dumping was done already in 2003, and that was done with visual inspection, so based on these decap photos. The later ones used various kind of techniques. I've dumped 2 boot ROMs, so I've been the first one in the world to do this. The Super Game Boy 2 and the original Game Boy launch version boot ROM, which is a bit different. It was only present for maybe, I don't know, 10, 15 weeks until they made a revision of that and changed the boot ROM. So yeah. So the boot ROM is the program that runs after you power on the Game Boy or reset it using a reset signal. The CPU basically starts from address 0. And the boot ROM is mapped to the first 256 bytes of the address space. The external ROM, so the cartridge ROM, the game ROM, is also mapped to that area and a bit bigger area actually, the first half of the address space. But the boot ROM always has priority if they are both active there. So when the Game Boy starts, it executes the boot ROM, not the cartridge ROM. And the cartridge ROM never gets any chance to execute until the last boot ROM instruction has executed. And this last instruction also happens to disable the boot ROM. So when the cartridge ROM runs, the boot ROM is gone. It's not mapped in the memory space anymore. So we can't read the boot ROM, the contents, with normal game cartridges. We need something extra to get an extra edge over the boot ROM unmapping. So if we manage to stop the unmapping, then we could just read it 1 byte at a time. So let's think about the different attack vectors we could use for dumping the boot ROM. We can't use a flashcard and test ROMs because, like I said, the moment when we get control and we can run our code, the boot ROM is already gone. We could investigate things with probing and soldering and do stuff with that. If we have desoldered a CPU and put it on a custom board, we also have full control. We can, with some techniques, read the boot ROM. And finally, like I explained before, we can decap the CPU and visually inspect it. Okay, so I'm going to do a demo of this. And I'm going to use the simplest method and the most non-invasive method available that works on the first and second generation Game Boys. So I think this was discovered originally by Ben Wen. It's a clock glitching method, and there's no soldering involved or anything like that. All I need is 1 wire and a flashcard to run some stuff. So basically, I've got this flashcard here. It's the EMS64. And I've got a special dumper program here. And it simply copies the first 256 bytes from the address space to the cartridge memory. So if the boot ROM is still active, is still readable, it will copy the boot ROM to the save file on this cartridge. If the boot ROM is gone, it will just copy. I've placed some zeros there, so it will just copy nothing. Okay. And I'm using this Game Boy, which has a backlight, so you might be able to see something. So this is a modded Game Boy. So first, I'm just going to run it without doing anything. So we get a sad face, and the reason is that the boot ROM was already gone. I didn't do anything to prevent it from being unmapped, so yeah. This time, I'm going to use this piece of wire to gently scrape one of the clock pins with a ground connection. So it's basically shorting the clock to the ground, but I'm trying to do it very gently. And this should glitch the clock so that it just confuses the Game Boy, and eventually it should end up in my dumper program without unmapping the boot ROM. Let's see, this might take a couple of tries. No, it worked. Okay, so it's not visible very clearly, but there's a sad face. It's scrolled down a bit. Sorry, happy face. And the sound was a bit different. So the dumper program detected that, okay, the boot ROM was still there. And now I will take this cartridge. And I'm just going to read the save file from the cartridge. And the save file is actually much bigger than the 256 bytes, so we need to truncate it so that it only contains the boot ROM. Okay, and let's see a hex dump. Well, there's some stuff. It's not zeros. And also, I've got a known copy of the boot ROM here, so we can check the MD5 sum, and we can check the MD5 sum of our dump, and it's the same. Yeah. So that was a copy from the real hardware of the boot ROM. All right. Now, when I had this talk at Disobey, I had this fine details section where I explained stuff about instruction timings and interrupt timings. But this time I thought we should do something a bit different. So we are going to take a look at the Globtop CPU. So you see those two CPUs. The left one is the B version of the original Game Boy. And it's the typical kind of chip. It's the rectangular black chip with all the pins on the sides and so on. On the right side, we have the Globtop version. So basically, it's just a big epoxy blob on top of a raw die, a silicon die that has these tiny wires. So this is a bit annoying from a research point of view, because there is no kind of no label of any kind. It's impossible to identify which version is this Globtop. In practice, I've discovered that it seems to behave exactly the same way as the B version. So maybe it's just the B version in a different package. In order to find this out, well, at least find some information about this, we need to decap the CPU. And first of all, we would like to desolder the components from the board. So there's quite a lot of extra components there. They are in the way. We would like to desolder them. So we can use a soldering iron, some solder wick to remove some solder, a hot air station to remove surface mount components. On this board, there's actually just one, and it's on the other side of the board. But yeah, hot air station is good. And if you have access to a desoldering gun, I just got mine a while ago. It's really good for taking out these through-hole components. For example, the cartridge connector, that big thing there, that's so annoying to get out without a desoldering gun. I've done it twice without the desoldering gun, and it just takes forever. Okay, so once we get all the components out, we can then focus on the chips themselves. And it turns out that this Globtop blob is a bit softer than the normal CPU packaging. And if you just heat it with hot air, you can use a knife to scrape it slowly off the board, and you can reveal the die inside. All the bonding wires that connect the chip to the board, they will get destroyed. They are too fragile for that. But if the main die survives, you can then do stuff with that. Okay, so I've got a video where I do this. This is actually not a Game Boy chip. This is from a printer that died, and I decided to use it as practice. So there's a Globtop chip there. Okay. So I bring in the hot air, and after a while, the epoxy blob starts breaking, and I can start scraping it away. This takes a while, and you notice that my stand is not very steady, so the board keeps shifting, but that's okay. So yeah, just keep getting the stuff out. And you can see the die already in the middle. And it's a tiny thing compared to the entire packaging. Most of it is just packaging and wires and the blob. Okay, almost there. Yes, and yeah, and whoops, the hot air blew the die off the board. Luckily I found it, so there it is. And that's the raw die with minor damage. This is very difficult to do without causing any damage. Okay, so that's how you can decap these laptop chips. So here's the same chip again, and there's an enlarged photo as well of the bottom left corner. Here's another chip. This one is from a Nintendo DS flash card that was a bit crappy. It destroyed SD cards, so I decided to destroy it. So I decapped it, and it's this 007 James Bond controller. I don't know who decided to give it this number. But yeah, it looks quite nice. But unfortunately, my microscopes are not enough to reveal the tiny transistor level details. So these photos look quite cool, but I couldn't reverse engineer the chip completely. You need more expensive equipment to do that. Okay, so after practicing with this printer, I went on and decapped and desoldered this board completely. So we started with something where there were actually 4 laptop chips, and in the end they were all uncovered. You can see that the RAM chips and the board around them took some damage. There's a lot of scratch marks and stuff. I practiced on them as well, so they didn't survive. And there's an amplifier chip here. It's actually not there, it's just like a metal plate there, because the chip flew off the board with the hot air, and I couldn't find it. But the most important thing, the CPU itself, it survived and it's there. Okay, so I also brought with me a USB microscope and the board in question. So this is the board I just showed. So we are just going to take a very quick look what it looks like in detail. All right, so I'm using this USB microscope. This goes to about 100 times magnification and costs like 100 euros, or maybe a bit less. So it's fairly cheap, and it's a good device to start with. All right. All right, so that's actually one of the RAM chips that was uncovered. Here's the other RAM chip. There's the missing amplifier, it's just a metal plate. And finally, we have the CPU. Okay, so one thing we are looking for in this CPU is some kind of label of the version in the die itself. So I showed you the Silicon Pron website decap photo earlier, and in the top left corner of that known decap of the B version, there is this text CESL20A. So if we can find the same text on this chip, we at least have some evidence that this might be the same one. Okay, so unfortunately, with this microscope, if we just increase the resolution a bit, yeah, and this is actually the other way around. Well, the label is over there. You can't really even see it. That's where the text is we are looking for. Okay, so this doesn't work out at all. However, I've got another microscope here. So this went up to 100 or maybe 150 magnification. But this other one goes to 470. All right, we see nothing, and the reason is that with these high magnification microscopes, it's very sensitive, and you need to get the exactly right height and focus setting to see anything. So I'm just going to see if I can get it to appear. Okay, we see something. It's very difficult to get a good focus with this. Let's see. No. Okay, now we are seeing some things. Just need to. It's not that corner. Oh, it's there. It's very difficult to get this in the right spot. Okay, the focus isn't great, but and the rotation is wrong, but it's there. It's there. So that is a 2. That is a 0, and that is an A. And the rest is unfortunately destroyed because the corner took some damage. But yeah, I've actually tweeted a better photo of this, so if you are interested in seeing the comparison between the known B version and this one, you should check my tweet. But yeah, it says 20A. So that's the suffix of the label we were looking for. So this is at least some evidence that, okay, this might be a B version. At least it has the same suffix in the chip label. And all it took was a bit expensive microscope and decapping and desoldering. But yeah, there's no other way. All right, enough of that. That's all. There's some links. I also tweet quite a lot about my findings and stuff if you are interested. And yeah, I'm happy to talk about Game Boys later if you have any questions or other things. I also repair Game Boys if you have a broken one. I don't just destroy them. Any questions at this point?
Yeah, what's the most difficult commercial game to emulate correctly?
Most difficult game, I don't think there's a single one. There's like, well, Pinball Deluxe was the most difficult for a long time. I think there's been one emulator that could emulate it, but that was by basically luck, because it failed pretty much everything else. So they just managed to find the right setting for things, and it worked. So I would say Pinball Deluxe maybe in general, but there's some other difficult games. Donkey Kong Land games are quite sensitive to timings. When I started developing my emulator, I played some of the Donkey Kong Land games on my emulator, and even like off by 1 errors in timings could just crash the game completely. And there's more. But yeah, I would say Pinball Deluxe definitely, even though it's sort of a solved problem now.
What is the? I'm just interested when you say timings. What are you needing to adjust, the number of cycles each instruction takes and that kind of thing, or cycles? Or?
Yeah. Basically, cycle or even edge, clock edge counts. The durations of instructions are actually very consistent and simple in Game Boy, because they are always multiples of 4 clock cycles. So we have a good understanding of how long are the instructions and how many sort of these big 4-cycle blocks there are. But the problem is that the PPU, the pixel processing unit, and the audio side, those actually work in terms of single clock cycles. So we need to think about not just how long is the instruction, but like the relative offset when things happen. So let's say you read memory, you read some pixel processing unit register. You need to understand exactly when in that like 4-cycle block things happen, so you can predict what the value that is actually read will be. And in practice, you don't necessarily need clock edge accuracy, but it's I think it's the best way to sort of have the most accurate understanding of the timings, because some things take like half cycles as well.
Do you make any videos at all?
You mean like on YouTube or?
Yeah.
No. I've got a YouTube account, but I've got some different stuff there, just some keyboard playing things. But I've thought about it, but it's quite a lot of work. I know there are quite a lot of people who would be interested in seeing some videos, but so far I haven't had the time from this actual research to focus on that.